Can you hear me?
I don't need to. Please don't need this one. Okay, so let me start my talk with a very straightforward but tough question, which is whether babies, you would believe, are conscious or not. I think that if you do a poll and ask people about this question today, you would get a very different answer from the answer you would get, like, I don't know, at the Royal Society 200 years ago or something like this. It turned out that our view on infants has changed dramatically, especially the last few decades, actually. And we tend to have much more empathy, to have much more, to attribute much more elaborate mental states to infants than we ever did. Just to give you an example, I mean, that's a famous example of the fact that infants went through surgery without anesthesia, some very deep surgery, until the 70s. Because basically the logic behind was that for certain surgeries, it was so dangerous to use anesthesia that it was better to go without anesthesia. And anyway, the baby wouldn't feel anything, or he wouldn't even remember. So it was still fine to do it that way. Of course, today this sounds very, very, very unlikely and unempathic. But when you think about it, we've been struggling into trying to find a decisive scientific answer to the questions of whether babies have a subjective experience, a conscious experience, some conscious access mechanisms, the way we do it. And fortunately, during the last decades, the last 2 decades, there's been a lot of work, especially from fMRI, but also from EEG, looking at how we can pinpoint some neural mechanisms, or at least some neural correlates of consciousness in adult populations. And over the last few years, what we've been doing in my lab was to try to basically take those neural markers or neural signatures of consciousness and other higher level process and try to apply them in babies to try to answer this very deep question. So the main problem with infants, you might say, is that they are unable to report about their own thoughts. And this is a very, very, very deep problem, because the main index for knowing whether someone is conscious or unconscious, even in adult population, is simply to ask them. So we know that babies, and especially research and development, has been showing that they have much more sophisticated and complex abilities than we previously thought. But we also know on the other side, as shown in the fields of subliminal perception, or in studying blind sight patients, for instance, that a lot of process can occur without awareness at all. So try to imagine a situation where you have, I don't know, like an infant fixating a red, very vivid ball rolling on a green grass. So what is happening in the head of that child is actually quite unclear. For sure, the baby somewhere in his cognitive system, in his brain, is doing some discrimination and actually reacting to that stimulation. But whether they would have the same subjective experience that you and I have when we're seeing this very red salient object actually is tricky to address. So just to give you an example, this is an old baby actually, but you see this child, you would probably think that this child is basically running after this red ball because he knows it's a red ball, he has a very vivid experience of what's happening there. But actually, when you think about it, it's not how you can find out. And this baby, which is a pre-available child, basically cannot really tell you about what's happening in his mind. So what is happening in his mind remains kind of mysterious. I'm going to give you another example, maybe, which is a little bit more convincing, about the red ball and green grass.
Grand final between Run Swift in the blue and Big Sid Kouider in the red.
So those are totally independent agents. They have some discriminative abilities. Able to see. So they're able to do those basically kind of sophisticated discriminations, acting upon it and so on. But I guess that most of you wouldn't give them any
high-level mental abilities or even attribute any conscious experience to those robots. So how do we find out? Oops. So what we decided to do is really to do an alternative strategy. We don't have access to reports, but what we can do is look at what's happening in an adult brain when they're reporting being conscious and see whether we can track the same correlates or neural signatures in infants. And here today I'm going to tell you about, so this is an example. So this is one 5-month-old infant participating in one of our experiments. We use high-density EEG, 128 electrodes, and we use them when babies are looking at some different stimuli. I'm going to tell you a little bit more about the kind of manipulation that we've been doing. But today I'm going to tell you mostly about perceptual consciousness, how we can basically use EEG and neural signatures to distinguish between conscious and unconscious processing stages in the infant brain. We also looked at prediction and surprise, and in particular, how predictions and how surprise actually links and shapes conscious perception. And finally, we've been looking at error-related conflict. And I mean, instead of looking at what happens to infants when they look at conflict around them, predictive error and so on, we looked at whether infants actually are able to detect their own mistakes, their own errors, young infants. So I'm going to start with the first question. And before I get to infants, let me just give you an overview of some of the recent findings in consciousness research in adult populations. So we know that perception triggers a two-stage process in the brain. During the first stage, basically what is happening is that you have an unconscious analysis of the sensory evidence coming to you. This is happening mostly in the visual areas of the brain, going towards the ventral and dorsal streams of the brain. And what is interesting here is that when you look at the profiles, this is time, and this is different stimulation durations. So this is time after stimulus onset. What is happening is that if you increase the stimulus duration, or if you decrease the masking strengths of the stimulus, so basically if you increase the energy of the stimulus, what's going to happen is that you're going to have a proportional increase in activity on those visual areas of the brain. So if you present a stimulus for 50 milliseconds, you get a certain amount of activity. If you present it for twice longer, you get twice more activity, and so on. So there's basically a gradual increase. And what is important here is that during this first stage, it doesn't really matter whether the stimulus is below the threshold or above the threshold of consciousness. If it's a subliminal stimulus, it's still going to activate your sensory regions the same way. The only difference is that basically this region is going to, those regions are going to simply care about the amount of sensory evidence which is received. But then, if the stimulus is strong enough, and this corresponds to, and if it crosses a threshold, basically what's going to happen is that the response is going to be more all or none. So it's going to involve some prefrontal, frontoparietal areas, which people like Stan Dehaene have been arguing to constitute the global workspace of consciousness. And then you're going to have a reverberation towards the visual areas, the sensory areas of the brain that you can basically see here during this second stage of processing. So in adults, it occurs around 300 milliseconds, and it corresponds more or less in electrophysiology to the P300 component. So here, it's more like an all or none signature. And this all or none signature is basically considered to be a very good neural marker of whether someone is going to be conscious or not at the end. So you can use it, basically, this all or none profile, this all or none late profile, you can use it as a neural tracker of consciousness. And then you can basically take it and try to apply it in infant populations. So the reason why here it's in between is simply because you average actually the trial. So sometimes on a trial-by-trial basis, it's seen or unseen at the threshold. Okay, so that's what we've done here. So we had babies watch some faces. Actually, we use faces because babies tend to actually like them, and it's much less boring than some other stimuli. But more importantly, the faces were presented in a masking stream, and the faces were presented for variable durations. And the idea here is to do the same thing. Look at how the amount of sensory evidence is going to impact your brain dynamics. And what we found is that in infants, the EEG shows exactly the same two-stage process as in adults. So here, you can see that there's only part of the result, but you can see here that there's a linear accumulation of sensory evidence during the first processing stages, and after, during a second stage, basically only certain durations, you have an all or none ignition pattern with certain durations leading to a strong negativity. This is called the late slow wave, the late slow negativity. And it was here only for the visible trials and not for the invisible ones. And we've done some other experiments with preferential looking to basically know what is the behavioral threshold of infants. And this turned out to coincide with those thresholds. So here I'm showing you the result it was for the 12-month-old infants. We've been able to go down even to 5 months, the earliest age we've been testing, and we found the same pattern, although it was more noisy and it was more delayed. So what is interesting here is that basically you have this signature of consciousness, all or none signature of conscious access, but the main difference with adults is that instead of having it start at around 300 milliseconds, it starts much later, at about a second. So it's a very, very slow process in infants. So here, if I take the longest duration, here of 250 milliseconds that we've been using, it means that the face starts appearing here and disappears here, okay? And still, after the face has been triggering some response, there's at least 1 second before we get this all or none response. So, in other terms, there's the same two-stage process, but it's just much slower to have this all or none ignition pattern in infants. Okay, so far so good. So another question we've been asking, actually jumping on this first study, was how predictions actually shape those neural components. And in particular, we've been interested in finding out whether the early brain regions, the early sensory responses, are actually modulated by prediction, or whether it's those late all or none ignition patterns, which are a neural signature of conscious access, that are actually mostly affected by infants' beliefs. So we know that surprise is absolutely crucial for learning. There's been some very nice studies by Fei Shu and others showing that infants do not just passively observe the environment, they are active learners. And we know also that they use surprise. What I mean by surprise is violations of expectations or violations of predictions as opportunities for learning. And probably Lisa Fagenson, who is here, is going to talk more about it on Saturday, but they've been showing in a very nice study recently that actually information-seeking behaviors and learning actually are mostly promoted by unexpected events. So, for instance, if you have two situations where, with one situation leading to a very consistent event, so here, for instance, you have a truck going down, it's supposed to be stopped by a wall here, but if you see that, it's fine. You're not going to manipulate so much that object, and you're not going to learn so much from it. But if you see this situation, after you remove this occluder, then babies are going to be very, very interested by that object and start to basically try to gather more information from it, and this presumably learn much more from it. So here we've been asking more at the neural level whether and how predictions modulate sensory responses, and in particular, as I was explaining, whether we're especially interested in whether they impact the early, supposedly non-conscious stages of processing, or actually do they have anything to do with the late stages associated with conscious access. So in order to do that, we use a very similar procedure. except that here we have faces and also some flowers, flower stimuli. So there was a set of flowers and a set of faces. And we presented them for a brief duration, but more importantly, what we had is that before the stimulus would appear, there would be a cue. So during the familiarization phase, you would have an arbitrary sound, something like doing boo, and then there would be a face afterwards. And during the familiarization phase, it would be 100% congruent. So whenever you would have boo, you would have a face. And when you had another sound like beep, 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 then there would be a flower on 100% cases. But then during the test trials, what we did is that we started to basically mess up with the proportions. In 2/3 of the trials, there were also a cue. There was also a cue, but which was valid in 75% of the trials, but invalid in 25% of the trials. So then they would receive the face cue with a flower instead of with a face stimulus. We also had in these test trials a baseline, basically, in which there was no auditory cue before the visual stimulus. Although there was a pre-mask to warn them that something was going to happen. So these are the results. So basically what we found was a little bit unexpected. That's the case here. So in the sense that we were expecting to have a violation of expectation effect, but what we found instead is that during the early processing stages, there's an increase in the visual responses, mostly for the valid trials. So the invalid trials didn't differ from the baseline trials here. So this shows basically that there's an early amplification of neural activity for the events confirming the prior beliefs of the infant. And we've been interpreting that as an effect of selective attention, with the idea that babies use their beliefs to basically filter out the world and focus mostly on what they think is going to happen. But then, very interestingly, when you look now at the late slow wave, the neural marker of consciousness, this very late response here, what we found is the opposite, that the late response was mostly driven by surprise. It was mostly driven by, there was a late amplification of neural activity for the unexpected events. So here, this can be interpreted as the fact that there's a global prediction error, a propagation of prediction error, or probably, or an update of prior beliefs, which is linked with conscious access mechanisms. Of course, we don't know whether surprise drives conscious access mechanisms or the other way around, or what is the interplay for now. But what this is showing is that basically predictions helps during the first sensory stages, and then leads to basically an update of prior beliefs, or at least the propagation of error signals in the brain. I'm going to turn now to the last signature, and this will be mostly a warm-up few slides for Louise Goupil's talk, which is going to be on Saturday on metacognition. But here I'm going to talk only about error-related conflict, and where we've been trying to address whether infants are able to not only detect conflict in the environment, but conflict, internal conflict that leads to, that is reflected by behavioral mistakes. So the question here is whether infants are sensitive to their own behavioral errors. And we in our previous study, but also there's a huge literature using behavioral paradigm, and showing that infants basically generate prediction error signals when there is a conflict between the predicted and the actual event. But an important question is whether infants are similarly sensitive to their own errors, which is here a conflict between the required and the actual response. And in order to address that, one way to do it is simply to look at a very well documented neural signature of error processing, which is the error-related negativity. So the ERN, error-related negativity, occurs whenever you took a decision and suddenly right after making your decision, you realize that you made a mistake. So when this happens, basically, there's a very strong negativity here of the frontocentral electrode, and we know that the locus of this effect is in the anterior cingulate cortex. And this is simply reflecting a conflict between the response you should have made, that you realize you should have made, and the response you actually made. And here you can see it here. So you can see that after the response, so here importantly, this is triggered, this is measured not after the stimulus onset, but after the response onset. So for instance, if you have to move your eyes toward the target, then we measure the error relativity at that stage. And you can see here, sorry, this is reversed here, but this is negativity on top. And you can see here for errors, this very strong negativity compared to the correct trials here. And it's an early effect, actually. It's at around 100 milliseconds after you made your response, and then suddenly you realize, oh, I should have gone the other way. And of course, that's because it's induced by some paradigms where you're pushed to make a lot of errors because things appear very quickly and are flashed in an unpredictable way. So here in infants, we use something very similar to our masking method. But here there were two. It was a gaze contingent paradigm in which whenever the baby looked here in the middle, then a face would be flashed, either on the one side or the other. And then there would be a waiting period until a reward. And basically, we've measured the threshold of infants, and you could categorize some trials durations here as either invisible or visible, and then we simply bin them in terms of invisible trials versus visible trials. But more importantly, what we did is, during this waiting period, we measured the neural activity of infants in between the waiting period and the reward. And what we found, so this is the four conditions: visible or invisible. So visible in plain line and dashed line are the invisible trials. So you can see that for the invisible trials, not much is happening. But for the visible trials, in red is the incorrect responses, the errors. And in green is the correct trials. And you can see this very strong negativity here. Negative response over the frontocentral electrode, which corresponds exactly to an error-related negativity. So the only difference is that here again, as in our previous studies, I told you that the ERN was generated at about 100 milliseconds after the response. Here it takes 300 to 400 milliseconds in infants to realize that they've made a mistake. So this is a very slow response compared to adults. So in other terms, this is showing that there's an error-related negativity in infants, demonstrating that in the absence of feedback in the environment, they're able to evaluate whether the response they just made actually was correct or incorrect. So this is a precursor of metacognitive sensitivity, we believe. Yeah, I didn't show that, sorry. So this is in the visible case, so this is correct versus incorrect. And you can see this very nice error negativity over the frontocentral electrode, exactly as you would see in adults. And of course, it's not here for invisible trials. So in conclusion, and I would like to maybe spend a little bit more time on discussing some of the perspectives. So the neural signatures in infants that we've been using have been demonstrating that there's a distinction between early non-conscious and late conscious stages of processing, doing perceptual processing, that predictions can bias non-conscious stages, while actually prediction error, instead of prediction confirmation, is what shapes the conscious processing stages. And third, that there are some basic mechanisms of internal monitoring, internal error monitoring. And Louise Goupil's talk on Saturday is really going to go deeper into that and tell you more about metacognitive sensitivity, but also uncertainty monitoring and decision confidence
in infants. So some remaining issues. I think that there are at least 3 very important questions that one can ask in infants in relation to this issue of consciousness. One is whether we can start to track contents and not just mechanisms of consciousness. So it's good to know that babies have some similar, albeit slower, but some similar mechanisms as we do, but it's unclear what is their content, the content of their subjective experience. So you know that a lot of people are trying to do that for dreams. They're trying to use decoding for trying to find out actually whether we can find out the content of dreams. And an important issue, an interesting issue for further research is really to find out whether we can, what is the content of what's happening in the baby's head. And that's something that we're trying now, although I must say it's quite difficult to use decoding approaches to find out actually what is, how sparse or how rich is their experience. And that's the second point. I think Alison Gopnik might talk about that. She's talking also on Saturday. There's really 2 different views on the richness, sparseness of conscious experience in infants. So on the one side, you have this lantern hypothesis by Alison Gopnik, arguing that babies actually not only have conscious experience, but actually they have a much richer experience than we do, because they're always in the process of learning, they're always basically facing novelty, and they have a much more restricted attentional filter than we do. So the lantern hypothesis is the opposite of what would be the spotlight for us, basically. It's diffuse. It's not clear whether that's the case, and this is related to a very deep issue, even in adult research, which is whether you can study access mechanism, or at least consciousness, regardless of the access mechanism that we use for reporting our experience. So that's a tough philosophical issue, but whether there is subjective experience which basically overflows what we can report, what we can say about it, is a very, very deep issue in consciousness research, and it remains unclear in infants whether they have such a rich, overflowing experience, or whether they have a much narrow conscious experience. So in our data, we've been following some neural correlates, neural signatures of consciousness that are more linked to conscious access by itself. So basically, in adults, it's what happens when you are manipulating and maintaining a perceptual content, but the more core aspect of subjective experience remains quite unclear. And finally, another issue that actually we're actively investigating right now is about self and bodily consciousness. So when you think about it, I think it's an underrated issue, because about 30 years ago, someone came with a test called the mirror test, and has shown that basically babies don't pass the mirror test before the end of their 2nd year of life. Hence, they don't have self consciousness before 2 years. And there's a lot of problems with this interpretation, which have to do with the fact that babies don't understand what is a mirror. It's not clear what would happen if you train them with a mirror, for instance, or it's not clear how they actually represent their own body, or how they represent themselves as a person in space and time. So this is another issue in consciousness research that I think deserves further investigations. And I'm basically done. Thank you very much.
Thank you very much. So we have some time for questions.
Hi, this is about the last bit about error monitoring. I was wondering whether you think that the negativity being later in infants, so 300... The negativity being later in infants, so 300 to 400 milliseconds. Do you think this is just slower processing, or is this more similar to the kind of classic N400 that just is more about general incongruency rather than your own error monitoring?
I think it definitely has to do with slow processing. Just because there's, the myelination of the long-range axons in infants is just like still very, very immature. So we know that there's slower processing in infants. So you would expect all those cognitive or neurocognitive components to be much slower. But what is important here is that they are the same. They're just much slower. What remains unclear, here we tested, for the ERN, we tested 12 months old. Probably Louise is going to talk more about it on Saturday for the other paradigms that have been used. But you can imagine that as long as they make the very first decisions, infants very slowly try to evaluate whether their decision was correct or incorrect. So it might be that there's some, implicit mechanisms whereby whenever they make a decision, the evidence continues to accumulate, and it accumulates very, very slowly, and you might just like go the other way and tell them that it should have been left and not right. Something. So it definitely has to do with the fact that it's slower, it's immature, but it's already there.
Okay.
So I have two questions. One, can you say a little more how you measure visible and invisible in infants? And the second question was about, so you've shown frontal recordings in the ERN study, but what about in the earlier studies with that slow wave? In adults, you can see it in frontal parietal electrodes. Can you see it in infants as well?
Sure. So regarding the first questions, in some earlier studies, not using EEG, using simply some behavioral paradigm, with Sophie Gelskov, we've been able to basically use some psychophysical thresholding experiments in which we presented faces, a little bit like in the last experiment. So you present faces at various durations, various masking strengths, and you simply look at whether they are chance or whether they look towards the face. So the idea that because they like faces more than anything else, so we presented faces on one side and simply a meaningless shape on the other side. So whenever they would see a face, they would react to that face. And by increasing the phase duration, you can see when do they start to look towards the face versus the other side. And this you can use to basically establish at which duration the face becomes visible. So that's how you establish what is the visibility threshold of infants. So this is done behaviorally, and then what we did is that we compared that to some neural signatures. So the only problem is that in these first studies we couldn't do both at that time because when you have EEG you're not supposed to move, so preferential looking doesn't work with EEG. That being said, it works with the ERN because for the ERN it's only after the move that you measure the ERN. So for perceptual consciousness we couldn't do it, but for the ERN we could do it. So the second question,
About frontal and parietal.
Yes. So that's a limitation of EEG, which is that you get a dipole, and you get activity in the when you get a negativity in the back of the brain, you get also a positivity in the front of the brain very often. So we couldn't infer anything from that. So what we do in those experiments is that we do a region of interest analysis. Here, in the first experiment, because we were studying perception, and because we relied on what has been done in adults, what we did is that we focused only on the visual areas of the brain. But for the ERN, because it's been specifically studied and located in terms of social construction in the anterior cingulate cortex, and using the fronto-central electrodes, then we did exactly the same thing. So that's the reason.
Yeah.
So you mentioned that the behaviors were correlated with the late neural signature. So were those? I guess the question that I'm asking is, what were the behaviors? And specifically, when you looked at something like looking time, the classic looking time reactions that are sort of information processing. Do you think those are associated with the later neural signatures, or might babies be showing signs of, say, deciding to look at one stimulus versus another earlier on?
Yeah, so the reaction time cannot directly be used so the baby behavioral reaction time cannot directly be used. The only thing that can be used to correlate is the sensory evidence, so the duration of the stimulus per se.
Okay.
So basically what you do, I want to make that clear. I think I was a little bit in advance, so maybe I can do it. If you look at, this is an illustration, but this is what has been found, in particular with MEG, but also with EEG, by Claire Sergent and Antoine Delcule and Stan Dehaene. Whoops. Yep. Yes. So this is really the case that here you can use masking strength, but this is the same thing as basically stimulus duration. So if you increase the stimulus duration, basically you're going to go from a subliminal subthreshold stage to a stage where the subject is reporting what's happening. So here, during this early stage, there's a gradual increase because basically your neurons, it's the first stage. So the neurons don't care about whether you're going to be conscious or unconscious at the end. The only thing they care about is how much face information do I receive, or how much stimulus information do I receive. So the more you give them, the more they're going to fire, basically. But here, what is happening is that if the stimulus remains below the threshold, what's going to happen is that the stimulus is going to fade away. So the stimulus is not going to be amplified. So remember, the stimulus here, usually the stimulus has disappeared. So the stimulus is not anymore in front of you. And what makes you conscious in a way is your ability to keep this stimulus in mind, maintain it, amplify it, act upon it, and so on. And this has to basically involve the frontocentral electrodes, which are going to sustain the information in the visual areas and probably do create our conscious experience. I'm not claiming that I have an answer for what consciousness is and how experience arises from that. But this first step is to find out what correlates with consciousness, what is a signature, and then use it in infants.
Yeah,
I have no idea what an infant actually do experience, but what is clear is that they have...
Yeah, it just, you mentioned something about that the late stage seemed to correlate with behavior in the infants, and I was just wondering, so what was the behavior? Am I right? Did you say that?
So yes, so it was related to the previous question about measuring behaviors.
Right.
So it correlated with some preferential looking studies that we've published before,
Okay.
in which the baby is facing a screen with two streams of masks,
Right.
and one face appears on one side or the other.
Okay.
And below 150 milliseconds
Okay.
or something, depending on the age, they just don't get it. So they are checks. They look on the wrong side as well as the correct side. But only after a certain duration, then they start to look at the correct side. And this duration is basically your threshold.
I see. Okay. So it's really a measure of so the point is that you start seeing this at about the same durations that you see head turns in a preferential looking experiment.
Exactly.
What's the relation between the preferential looking measures and say something like just dwell time, or I guess it's hard to tell.
It's hard to tell because the problem is that they're also slower in terms of motor movement. They're also slower to react. Even if it's fully visible, they're going to be much slower than adults. So then we can only look at the sensory evidence and not the motor response per se. But that's unclear. Actually, the ERN says a little bit, something about it, by the fact that they're super slow to detect that they made a mistake. So the way it's done is that it's the same thing here, sorry.
Yeah.
So this is what happens in adults. So you see, an adult is presented with a target stimulus on one side or the other. He has to quickly go to one side, but then right after they move their eyes to the incorrect side, poof, you have this very strong response. It's even before 100 milliseconds. But here you can see in infants, here, it's much slower. Actually there was a little trend here, but this was not significant at all. But here we have this very strong, very significant effect occurring around 400 milliseconds. So much later, about 3-4 times,
Right.
exactly like in the perceptual consciousness studies. Here for the error-related signal, it's the same thing. They're just much lower.
So I guess the theoretical question is this, are you looking at a signature that's related with specifically motor behavior, with producing a motor response? Or is it, so there's detection of the stimulus,
That's a very good point.
but there's also updating of beliefs, for example,
Yeah.
which is something that we know that babies are,
Yeah.
we know that babies are doing a lot. And
Yeah.
Amanda Woodward just gave a talk recently where she was suggesting that some of the differences between, say, what you see in looking times and what you see in motor behavior might be due to the fact that it takes babies a long time to get a motor response organized. So the question is, there's one thing which is registering the information, there's another which is actually updating other representations, and then there's a third thing which is actually deciding to do something based on that information. So how do you think those are related to what you're talking
Sure. So the deciding to do things, it's not supposed to be involved here because it will occur afterwards. And in adults, we know that the ERN is related simply to the fact that you detected that something is wrong. It's not deciding that because something is wrong, I have to do something else. But this is a good point here. They might be slower simply because it takes them much more time to just move to the one side and then they decide, because the behavior is slower than because this is a post-behavior effect. It might be related, this slowness might be related to the slowness of the behavior and not of the error signal. But still, there is an error signal. That's a good point. They might be slower just because of it's a post-behavior effect or because they're slower at accumulating evidence telling that they made a mistake. Yes. Thank you.
Okay. Since we have a little bit of time, I'd like to ask one question. The concept of surprise seems to be central in this work. In one of your slides, I thought I understood that the way you actually conceptualized this was prediction error equals surprise. Which from the point of view of many mathematical models is a bit unconventional, since not all things that violate your expectation are actually surprising in the way we use the word surprise in everyday language, and that's why many models model surprise as prediction error in the case where you had high confidence in your prediction, but prediction errors where you had low confidence are not surprising at all. And so, am I right to understand that this is your way to view surprise, and how do you see this choice of conceptualizing surprise impacting the analysis or even the design of the experiment?
Yes, so it's true that here we're looking at prediction error signals that we call surprise simply because they are violations of expectation. But it's true that they're also conflating your confidence. But the fact that we got those neural signatures mean that probably, even if there was confidence involved, probably confidence was involved as well, because otherwise we wouldn't get any prediction error effect. But still, this still has to involve some computation of prediction error at one stage. So this is just the first study aiming at showing that basically babies use prediction to confirm what's happening, try to confirm their prior beliefs, and then generate an error signal. So to answer your question, I actually don't know what is this error signal corresponding to. We could, for instance, generate some probability such that there would be a violation, but where there would be low confidence, although it's not clear how you would do that, because each time they're looking for it, so if there was no confidence, well, they wouldn't even give up. So now we have a very basic way of defining it, which is simply violation of expectation. So surprise is violation of expectation. Whether this involves confidence, whether this also involves prediction of rewards, for instance, this is unclear. But what is clear is that they generate error signals that correlate with the conscious experience.
Okay, so thank you very much. Let's thank the speaker again. And so our next speaker is Matthias Gruber to continue on neural